I'd like to welcome everyone to the Friday afternoon session of the 2026 uh, Brown CFPU AI Winter School. This afternoon's module will be led by James Verbis, and James will tell us about reinforcements learning for orbital transfers. So take it away, James.
Thanks, Jan. And I believe everyone has access to the Google Drive. So in
Oh,
this particular section, there's a folder called Verbis Reinforcement Learning for Orbital Transfers. So I'd encourage you to go check out that directory.
yeah, I forgot to point out that you should, as with all the other modules, make a copy of the module on your local drive because you won't be able to edit. You only have read access to the one on the shared drive. Um, if problems persist in reaching that module or any other questions show up because of the webinar format. You should put questions in the Q&A, and I will try to pass them on to James as they come in. Okay. So,
Thanks. And that directory should be here in the winter school under Verbis Reinforcement Learning for Orbital Transfers. And you'll see the media for this workshop in that directory. So there's some slides we're going to go over first, and then the Python notebook that we'll be using Google Colab to run second. And that is the one without the word example. So that's the one to check out. Um, okay, so let's get started. I'm going to share my slides um, here. All right. Yeah, so I'm going to be speaking today about using reinforcement learning to learn a simple orbital transfer problem. So this is chosen kind of as a concrete reinforcement learning sandbox so that we can explore kind of how to design these types of missions and then how to turn kind of a known physics problem into a reinforcement RL problem and debug the policies to show you all how that works. So I'd like to thank everyone, Ariel, Chongwen, Rick, and Jan for coordinating the workshop, for providing feedback, and for inviting me to contribute to this contribute this session. So I spent many years working in the physics department at Brown as a graduate student from 2009 to 2016. So sort of the left image and the top image show kind of that period. And I was working with Rick Gateskill, looking for dark matter. And I transitioned to industry in 2017, where I went to work at LinkedIn in the trust organization. Um, and I've been there ever since. So for almost the last 10 years, I've been working building machine learning and AI models to detect and prevent abusive behavior on all LinkedIn surfaces. So that's things like finding and removing fake accounts, um, detecting when bad actors try to hack accounts and stopping that or fixing it in the rare case that it happens, or detecting bot activity like abusive automated activity or doing content moderation. So it's very heterogeneous, and a lot of the numerical and analysis techniques and mindset I learned in physics transitioned really well into detecting abusive behavior at LinkedIn. Um, and one such example is in the physics world, I spent a lot of time worrying about rare events and detecting a needle in a haystack looking for dark matter interactions in our detector. And similarly, now I look for the rare cases of abusive activity that tries to blend in the large ocean of normal legitimate user activity on LinkedIn, which has over 1 billion members. So from that from that example, you can kind of see how some of the techniques and some of the approaches and mindset could carry over well. Um, so in this workshop, you'll learn a few things. So the first is to build some physics intuition. So we'll kind of do a review of very basic orbits, and in particular, Hohmann transfers as an analytic baseline to go from one orbit to another in a two-body system. And kind of when that works, when it breaks. And then we will formulate reinforcement learning to solve the same problem. So Holman is an analytically solved problem, but we can use reinforcement learning to teach an agent to basically learn how to do something similar, and we'll see how close we get to the ideal solution. And then we're going to play around together on actually training and debugging some of these reinforcement learning agents using different types of control mechanisms. It won't be perfect, but the idea is to go through the process and see how close we can get to the analytical ideal. So we'll be able to diagnose some of the failure modes and then iterate. And at the end of the session, there's going to be the opportunity for you to take what you've learned, use your intuition, and update some of the parameters in a reinforcement learning training scenario and see if you can do better than the examples that I provide in terms of getting close to that analytic Hohmann ideal. So at this point, I'm going to make a bit of a transition. We're going to jump into the notebook just to get things kicked off so that everybody can get their notebook running because it does take a little bit of time to run. So I want it to start running in the background um, while we go through the rest of the slides. So I'm going to change my screen here to the reinforcement learning notebook. So as I mentioned, it's the IPython notebook that does not say example, is kind of the sandbox one for the workshop. So I have that open here. And at this point, we're going to walk through it later, so don't worry about the content. But the key here is to run the notebook to get it started and just run all the cells. And one thing I have noticed um, so it does take maybe 20 to 30 minutes to run. One thing I have noticed, if you do have an educational Google Colab account, which I think some of you may from prior sessions, if you're at an educational institution, it does run a little bit faster on the TPU setting. I think due to the fact that these actually have better CPUs, since this is a CPU dominant task. But basically, if you choose this, if you have the option, that might get maybe a factor of 2 speed up compared to the CPU. So I'd suggest doing that. If not, CPU is fine as well.
I know some of the participants were able to access the T4 GPU as an alternative. Is that better than the CPU, or is it about the same as the CPU?
So I haven't tried all variations. I would suggest trying the T4 TPU if you have
Okay.
access to it. Um, I the we're not really benefiting from the parallelization in this particular notebook because it's CPU limited. But my hypothesis here, just from experimenting a little bit, is Google cloud probably has better CPUs, like newer machines for the machines that have these advanced GPUs. So that's where we get the speed up from. Um, so I would suggest using that if you can. If not, CPU is totally fine.
And again, if you have any issues getting to a copy, uh, please put a question in the Q&A, and we'll try to debug it as we go along.
Yep. And then so once you've changed your runtime, just press run all, and it should start running. It'll install the required dependencies if any are missing, and if things start to execute, you should be in good shape. So we will revisit this at some point during the slides, and then of course at the end of the slides to go in a little bit more detail. So don't worry about it now. As long as it starts running, you should be in good shape. Okay, so returning to the slides. Um, I want to give a brief refresher on orbital geometry. And one way you probably recall um, learning about orbits is based on a geometric description with semi-major axes and eccentricity and different orientation angles. Um, so this is a little bit complicated for our use and not the most useful set of coordinates. So we're not going to use these in detail. We're actually going to um, simplify the problem a lot by just having two bodies, where the central body is a point mass. Um, that's the dominant mass. So we can assume small m, the satellite is uh, de minimis compared to the mass at the center, and that'll give us the mu equals gm gravitational parameter. And then, there's no additional complications we're going to assume that would be present in real life. So things like J2, which is could be due to a non-spherical shape of our central mass, atmospheric drags, or, third or more bodies in our system. Because that would be a level of complexity that's beyond what we're looking for this demo in the workshop. And I think the other thing to take away here is just to recall that, semi-major axis kind of describes the size of the orbit, and then eccentricity describes the shape to some level. And we'll go into a little bit more detail on these. But basically, making these simplifying assumptions and the fact that we're going to be two-body um, simplifies a lot. And we're going to go actually one further and not just be a two-body problem, but we're going to be planar. So basically, we're going to be only looking in orbits in the same plane, so it becomes a two-dimensional problem. And if we look at it in terms of energy, we can relate the um, mass and the semi-major axis to the energy normalized. In this case, it's normalized by the satellite. It's per unit satellite mass, this small e here. Um, but you can see it's just a function of the gravitational param gm and the semi-major axis. And then also the eccentricity is given here by the angular momentum L as well as energy and mu. Um, so just to be clear, and maybe you recall the total energy equation, GMM little m over 2a from your mechanics classes. In that case, all we're doing is multiplying this small e by the satellite mass, and then we can recover this. So using this, so we are going to be using these eccentricities and energies and angular momentums a lot because it turns out that that works well in 2 dimensions. Those are the kind of physical parameters we'll care about for our problem. Um, and these are described in a little bit more detail on this slide, where basically during the coast phase, the reason we care about energy and angular momentum is that they're conserved. So not a surprise there. Um, and the energy parameter, again, here can be rewritten as just a function of the velocity, the magnitude of the velocity, the radius, and the mu, the gravitational parameter, and then angular momentum is, of course, just the function of radius and tangential velocity. Um, so these are just the second bullet here is just the same equations from the previous slide, basically relating semi-major and eccentricity to the energy and angular momentum and mass terms. And the real takeaway here on this slide is that um, we can ignore those phases, the angles and phases, and go use energies and angular momentums to be completely rotation invariant for our modeling later. So the parameters that you'll see coming up over and over later are the radius of your orbit in the 2D plane, the radial velocity, the tangential velocity, and then, we also, it's somewhat redundant here given these equations, but we also use the energy and the angular momentum. Um, so those are, of course, rotationally invariant as we move around in our orbit. Um, so those are convenient. Um, so the problem at hand is in a 2D plane, we have two masses. One is the central, big M, which is dominant, and then an orbiting small mass. And the small mass is at radius r1, and we want to get to radius r2. So we want to change the radius of that orbit. And once we change that radius, we want to have the new radius be near circular. So that's a small radial velocity. Um, and there's some constraint on this problem because you can imagine there's probably lots of ways to get there. But in practice, what you'd want to do is minimize your fuel, minimize the amount of fuel you use to get from R1 to R2. And you may recall that actually for um, small burns of your spacecraft in this transfer scenario, fuel is proportional to is delta V, so change in velocity. So we can use throughout the rest of the talk, we're not going to be talking about fuel. We'll be talking about the total delta V, the cumulative delta V we do during the orbit transfer. And we want to minimize that because that is a proxy directly proportional to our fuel. And just to remind everyone where that came from, there's a kind of a famous rocket equation where I and G here are just constants. I is related to your particular engine. G is to convert the units, it's gravitational constant. And then the M0 and MF are just your initial and final spacecraft mass after your burn. So you lose some mass as you burn. And then, of course, for very small delta M's during the burn, you can do some Taylor expansion and manipulation here, and you get the relation where the change in mass is meaning the change in fuel is proportional to the change in delta V, apart from these constants. So that's where you get that fuel is proportional to velocity change. Um, so again, the takeaway from this slide is we've got a really simplified case, and then we're going to be using delta V as our constraint that we want to minimize for our orbital transfer from R1 to R2, and delta V is basically our fuel use. So in this slide, we talk about the analytic ideal. So again, this is something that I think many of you might remember from mechanics. And this is the analytic benchmark we'll be comparing all our later work to. Um, so in this case, we're gonna set up a transfer for our circular orbit, R1 to at R1 to R2. So again, we're in the same plane, and we want to do burn our engine in some way to get from R1 to R2 for our spacecraft with mass little m. Um, so Hohmann transfers are a famous solution to this, which can be solved completely analytically and only require two burns, which um, to get from R1 to R2. And the transfer ellipse for a Hohmann transfer shown in the solid red here. So initially your spacecraft is orbiting clockwise at R1. At some point you do a burn um, where you change the energy, or you change the velocity by delta V1, and then that kicks you onto a transfer ellipse shown in red. And then once you get to the target radius, you do the second burn, both prograde, by the way. So they're both in the direction that the spacecraft is traveling. And you do that second burn, and then that locks you in stably on your target R2 radius. So basically, the maneuver is one burn at R1, impulsive. You coast for half the transfer ellipse, and then another burn at R2, and then you're stably on R2. So why we're using it here, it's great for kind of a fully solved analytic ground truth baseline where we can use to compare our simulation and reinforcement learned solutions to. Um, However, real missions are often much more complicated. You often have, not perfectly circular orbits. It's in three dimensions, obviously. There may be other constraints, more bodies, more than two bodies in the system. And there might be some other constraints like how big of an impulse your engine can provide. So in those cases, you need to do something more complex. One option could be a learning or reinforcement learning solution, and we'll talk about that a bit later. So on the bottom of this slide, there's a bunch of equations. The takeaway from these, I think we don't have to go through all, but the key ones to look at are the delta V1 and delta V2. Um, so basically, this tells you how big of a burn. Remember, change in velocity is fuel. So it tells you how big of a burn you need for the first impulse and the second impulse. And the takeaway here is that it's purely a function of the mu mass term as well as the initial and final radii R1 and R2. So this is where you can see, hey, it's analytically solved, and then you know, hey, I can burn at burn one at initially at R1 with delta V1, burn at R2 with delta V2, and then you get on the right orbit. The other thing to point out here that we saw earlier, we mentioned the normalized energy per unit spacecraft mass, the script D, at each coast phase, so at R1 as well as on the um, transfer ellipse, as well as on the final orbit, we can calculate the energy, and these are just functions of the radii and the mu mass term here. Um, so this should the takeaway here is that it is um, analytically solved. This is a good textbook baseline that we can use to compare our numerical simulated model-based solution to later. Uh, so as I mentioned, real missions require more general methods. So again, Hohmann's optimal for these kind of ideal cases of circular orbits in the same plane, two bodies with just these impulsive burns. But when you want to do things that are more complicated, um, with 3D geometry, more advanced physics, more constraints, and uncertainties, um, it becomes more complex than just a closed form analytic solution, and that's where RL in the could be a good solution here. Um, you know, Another case where kind of an edge case where Hohmann starts to break down is if the R2 is much larger, I think greater than or equal to 12 times larger than R1. And then in that case, there's kind of special cases where three burn solutions can beat Hohmann in terms of efficiency for fuel use, but they take a lot. They may take a lot longer to actually do the transfer than Hohmann would. Um, okay, so moving on beyond this analytic solution, I want to give some intuition about reinforcement learning. Um, so this is kind of a cartoon example where we show the same problem in this diagram. We have an R1 and R2 um, orbit, and we want to get from R1 to R2, our satellite mass, little m. Um, but instead of doing it analytically, we want to learn it from trial and error in a simulation. And you could imagine your spacecraft has a controller, which says, which we're going to represent as pi here, but it basically says, hey, given a certain state, which means where I am, how fast I'm going, what orbit I'm on, it could be a number of parameters that you use to describe that state. What is the best next action for me to take? Is it to burn? Is it not to burn? What direction to burn? Um, and you could imagine creating a controller which, given a state, does an action that could give very good performance if it always does the correct behaviors to get a good efficient orbital transfer. So our goal basically for reinforcement learning is to learn this feedback controller given the current orbital state, what is the next action to do, and do this via simulation in a trial and error way. So there's kind of two roles here. There's the agent, the spacecraft controller, which is the pi, given S what action to take. And then we also need to kind of create a little simulation environment which has the physics baked in for this 2D orbital problem. And the core idea here is to have your agent observe a state, choose the next state at time t, choose the next action to perform at time t, provide that information to your uh, simulator, your environment, which will return, okay, given the state and the action the agent took, what is the next state? So, um, and then use that to update uh, and make the next decision with your agent. So it's kind of this iterative process where you simulate trajectories. Um, and in this diagram over on the right, we show kind of many trajectories that you could imagine if you start your orbital transfer at R1. Some might um, burn in a way which causes you to crash into the central mass, big M. Some might get you, and that's shown by one of these red trajectories. Some might get you to the target orbit, but in a way that's not efficient or not stable once you get there. Um, and then some might cause you to, your orbit to blow up and you shoot past your target orbit. And of course, the ideal Hohmann was described in the blue case here. Uh, so how do we do this in practice? We're going to simulate many of these trajectories and use that to learn what the right policies are with our for our feedback controller. And eventually we're going to get this neural network artifact, which given a state will tell us the right action to take to get um, efficient close to Hohmann like transfers um, between R1 and R2. Um, Okay, so we already kicked off the training, but we can quickly check in and let's just see how it's going and make sure that everyone's training run is going well. Uh, so I'm gonna switch screens over um, just to take a look at that.
Just a reminder for those of you who joined in a little bit late, going to the Google Drive that's in the shared drives. You should all have access to it. Make a copy of the module of the notebook that's in the Verbis module, the one that doesn't say example, and then if you can go to runtime and set the CPU to the T4 TPU, that seems to be faster. But set it running because it will take a little bit of time. And those of you who've gotten it started, can somebody post if they've actually how far they've actually gotten?
Yeah, it would be in the Q&A if if it's successfully running, it should still be running. But if it's successfully running, please let us know. If you're running into a problem, there's any errors also, that would be good feedback to know in the Q&A. Um, but I can summarize sort of where mine, I kicked it off at the beginning of the session with all of you. I can summarize where mine is. Again, we'll go through the notebook in more detail, but basically, you should see some of the plots to be starting to be created. There's many experiments we'll do. So some of them have finished, and you see the plots. And we'll go in more detail on what those are later. And then some of them um, are probably still running. So you can see here you're getting some updates here with your logs. So basically, you should be, maybe your experiment one, experiment two are
It
probably
looks
done
like
at this point, and experiment three is going.
Yeah, it looks like some are on experiment two at the moment.
Sounds perfect. Okay, yeah. And again, depending on which instance type you were running on in the cloud, it may run a little bit faster or slower, but that sounds about like the right rate of progress. Okay. So let's while that continues to run, let's go back and talk a little bit more about the um RL details in the slides. Um, so I'm gonna go back and share my slides. Um, okay. So this kind of gave us some intuition about what's happening. But this slide goes into a little bit more detail. It's kind of like the reinforcement learning generically in one slide. Um, and again, we're not going to go into like all the details, but this should give a high level gist of what happens in reinforcement learning. And this is a famous diagram on the right from a kind of a classic textbook for reinforcement learning. And as we mentioned, we kind of have two things. We have an agent, which is our controller in our spacecraft, which is determining when to do burns, to do these orbital transfers. And then we have an environment, which in our case is our physics, our simple toy physics environment for orbits. And we'll go into the code of what that looks like in the notebook in a bit. But basically, it's uh, you know uh, the physical system with the masses and doing some uh, physical doing kind of trajectories of being able to simulate trajectories given that physical system. Um, So once we have the agent in the environment, as I mentioned, our agent takes in the state and the reward at time t. And we'll talk a little bit about these rewards in a bit. But basically, so the state could be things like what you know now. So the radius, the radial and tangential velocities, the energy, the angular momentum. So those are kind of like variables about your spacecraft. And then maybe what time step you're at or what the last action was can go in. And the agent can make a decision on that, given that information, to do an action at time t. So that's kind of what we do next. So that's what kind of burn, what do we do at time t. Now, your agent provides that action to your environment, which knows the state, and the environment is going to return information to use in the next time step, which is the t plus one here. And the environment calculates, okay, given the current state, meaning your spacecraft parameters and orbital parameters, and the action your spacecraft took, what is its next state in the next time step? So that's pretty straightforward. And then it's also going to return a reward, which kind of is a measure of how good this state is, how good the situation is. So that's the R here. And our goal overall in reinforcement learning is to maximize the long-term reward. And there's a lot of ways. Right now, this is high level, but there's a lot of ways of determining what is good in the RL case. And there's a lot of creativity you can how you can define this. But at a high level, it often looks something like this, where you're going to sum over for many trajectories, you're going to sum over all time stamps in the trajectory, summing up the rewards. And then there's a gamma factor here, which is typically we're going to use something very close to one. But you can think of that as like you can see it's to the power of t. So it kind of tells you how to discount long-term things far out in the future. Uh, so like if for many timestamps way out in the future, if you have a fraction less than one, obviously those are going to count way less. So it's kind of like a measure, a way to discount behaviors later compared to short, earlier behaviors in your trajectory. And this is what we want to maximize. Um, and what we learn again is that policy. So it's given a state what action to take. Um, and there's kind of two at a high level, kind of two common ways to do it. Um, one is we learn is a function called Q, which is given the current state and the action, given a state and an action, it tells you how good that is. Basically, what's the reward, and you want to choose the action that maximizes that function. And the other, which is the type of reinforcement learning we're going to use here, is actor critic, which is you learn the actor, which is the pi function we've been talking about, which is given a state, do this action. So it's like given a state in your system, this is the next action our simulation is going to take. Um, and then plus a critic. So this is usually just a function of the state, and it just says how good is the state. So the better the state, the better that'll be measured in this function. So you give it a state, and it's going to tell you how good the situation is. So at a high level, don't worry too much about these like a functional form for these. These are actually black box neural networks for our purposes here. So, the pi and the v of s, these are actually neural networks, and we're going to learn, given a state, it's going to spit out the action, or it's going to, spit out the value of how good the situation is. But those are the things that we're actually going to be learning, given many simulations runs. And so one we can go into a little bit more detail. So this is kind of a high level, I would say, like it's a little bit concretely grounded in our orbital case with the state and action information, but at a high level, this is how reinforcement learning works. To make it a little bit more concrete for our orbital problem here, um, we can talk a little about each one of these parts of the diagram. So basically, the environment we have is kind of the physics simulation, and the mission we have, which is a 2D, two body uh, orbital transfer problem going from R1 to R2. We know the masses, and it's all in the same plane. So like that's all defined and is just physics. Um, Then what is the observation our agent makes? Like what information do we want to give the agent to allow it to make a smart action decision at time step t? Well, we're going to give it the radius r. We're going to give it the velocity, radial velocity v of r, the v of t. And then we actually know, if you recall from our earlier slides, we actually know at a given radius, like our R1 and R2, we actually know the angular momentum and we know the energy at those. So at the initial and the end. So we can actually, and we can calculate those at any stage given the spacecraft's current state. So we can have the agent observe terms that are how far are they away from the target angular momentum and energy. So that's kind of allows it to get some measure of how wrong it is or how good it's doing. And then the other thing we're going to give it is the last action it did. So at state t, it knows the action it did at t minus one. And the reason we do that is it kind of helps to make to learn smoother policies. So one thing to note, and we kind of deliberately constructed this, if you recall from the earlier slides, there's no angle. We avoid all of the complexity of angles because all of these things are rotationally invariant. Um, so basically, we really simplified the problem by having circular orbits, choosing coordinate like these features that are rotationally invariant, um, and having it all be coplanar. Um, so given that information is kind of the state provided to the agent, what actions A of t can the agent do? Uh, so it's going to do burns, but even there's creativity in terms of the way we set up the problem. Um, in terms of the types of burns that we can do. So, I made some choices in creating this toy example um, to either do discrete burns or continuous burns. You can, make it arbitrarily complex or, depending on your interest level. But basically, there will be two examples we show in the notebook. The first is discrete, which is basically the agent learns I can either it's kind of three options it can do. It can coast, it can do a prograde burn with plus dV magnitude, so just a constant at each time step, or it can do a retrograde burn. So it can, and there's nothing else it can do. So it in this case it's kind of a simpler problem because the action it's got to learn just one of three things. It's do I coast given my state? Do I do a prograde burn or do I retrograde burn with some fixed magnitude that is set? Um, and then we'll do a little bit more complex one where we allow it to be continuous. So basically, it's similar. Um, at each step, it's going to make a decision about the burn, but now it's actually going to learn, it can throttle up and down the size of the burn at each step. So it can go, the delta V is set again by this dV magnitude constant, but you can choose any float, between -1 and 1 and multiply it by that. So that the agent's going to learn not only the direction of the burn or maybe something close to zero to not burn, but can do any magnitude in between. So those will be the two examples we use. And then another place where there's a lot of creativity, which I made some decisions and you'll get to play around with a little bit in the notebooks, is in the reward. So how do we, the R of T here. So how do we calculate the reward? So, well, there's a few things we want to do. One, we want to reduce the errors in angular momentum and energy, right? Obviously, we want to have be more rewarded the closer we get to the target energy and angular momentum. Um, we can also add some other things. So, for example, we should probably have a penalty on delta V because if you just have a reward about getting close, it might not be very efficient. You might have do a lot of burns, use a lot of fuel, get to the perfect um, final state, which where you've minimized the error in energy and error in angular momentum, but it might be not efficient. Okay, so we want to have a penalty term for delta V. So we want to minimize that. Uh, the other thing that I chose to add, but again, there's some creativity here, is a penalty on ignitions. So, you want to make the spacecraft be judicious about how many burns it does. Especially if you're trying to see how close you can get to that Hohmann ideal of two burns. So I added a penalty on ignition, and then there's also some penalties on crashing or timeout. So if you remember that figure we had a few slides ago where there's a blue trajectory, which was the ideal, and some red failed trajectories where it crashes either into the central mass or spirals out, and kind of blows up the orbit. Those would result in either crashes or timeouts. You want to penalize that really negatively. So that gets penalized when a sample trajectory, simulated trajectory ends up like that, you want to penalize it so the agent learns don't do that, right? Uh, you know, Similarly, um, you can give a reward on success. So like let's say you solve all of these. Maybe there's a bonus to help your agent learn once the simulated trajectory gets into the target band within some tolerance, give it a reward so it learns, hey, this is good what I've done. So it kind of makes it more unambiguous, and when you're running many simulated trajectories, which ones are good or which ones are close to good. Um, so what we actually tune, so basically all of this is in the code, which we'll run through. But what we tune is parameters like how much we do the penalties, how big of a burn we can do, um, what the tolerances are for some of these bonuses, how many training steps, and we'll play around with some of those later. And then also, playing around between discrete and continuous. Okay, so at this point, we can conclude the slides. This is the last slide. And basically, it's just a summary of what the takeaways are and what we're going to do next in the notebook. So The key takeaways here is that Hohmann, for our toy example, is the benchmark. It's analytically solved, closed form, gives you the fuel optimal solution for the ideal case where you go from orbit at R1 to orbit at R2, using only two burns. However, in practice, reality is a lot more complex than that. There's perturbations due to atmospheric effects, due to the other masses in the system. So due to the 3D geometry, non-circular orbits, etc. So, in practice, things are a lot more complicated than this, but we're doing it for a simple example. Our goal is to learn a feedback policy by trial and error. So given a state, what action does our spacecraft take? And you could imagine, we'll be just doing it for the simple case, but you could imagine that strategy could be done for complex spacecraft planning, trajectory planning. And what we're going to do next is go into that notebook and iterate, look through what happened, look at the code, and iterate experimentally, and then choose and kind of look at why we chose some of these encodings and costs, look at some of the failure modes or what could have been better. And then also at the end, you'll get to play around with some of these parameters and see if you can beat the demo cases I provided. So there's a form here in the slides, so you can click into this link. Please do mention in the Q&A if you can access it, but you should all be able to access it. And at the end of the workshop, or during, feel free to submit your experimental results. And if folks are able to get to the end, we can take a look at some of the submitted results and see if anyone's able to do better than uh, do better than what was shown in the demo.
Just to
Okay.
remind you, the slides are also on that same folder of Google, um, in the Google Drive. So you should be able to open the slides and click on this link.
Yep. Yep. Thank you. Okay, so I'm gonna switch over to the slides at this point, or the notebook at this point. Um, so here it is. And I'm going to walk through just to give people context because I think it's important and valuable to kind of see, like in practice, this is a completely self-contained demo in this notebook. I think it's valuable to see in practice what, how we set this up. And I'm going to experiment here with a slideshow view. I think it is a little bit clearer for folks. So please let me know if um, if you have any problems following. Um, okay, so basically this just allows us to walk through cell by cell in the notebook and have it blown up a little bit more clearly. So what this notebook is about, this is about what we were just discussing. We're going to show three cases that are completed. One is the analytic Hohmann transfer solution, and we'll show some plots and what that looks like. And that is also going to function as a validation of our physics, our little toy simulation environment, because we're going to apply that to the analytic Hohmann transfer burn solution and show that it gives us the right trajectory with our simulation. And then we're going to do two reinforcement learned agent solutions. So one is the discrete case where it can only do coast, full prograde, full retrograde. And then the third is a continuous RL solution where it can actually choose a smooth throttle between minus 100% and plus 100% at each time step. So again, it's not going to be the optimal solution on the first try probably for these, but it's going to, in practice, we can get pretty close to optimal. I've given the way that I've fine-tuned the parameters for the run. But the real key that you should be taking away here is kind of what the workflow is for running experiments, how to do the RL training, how to understand the failures, and then how to repeat. And then finally, you can control. We'll do this exercise where there's my experiment at the end of the notebook, where we're all gonna edit and then run it, and see if we can beat some of the demos. Although it's pretty hard to do, so we'll see. Um, okay, and one other thing to mention in this notebook is it's a little bit hard to get completely deterministic behavior. So there's a lot of random seeds and the not only the simulation but also the um, reinforcement learning, the neural network learning, and then also especially if there's some parallelization being used for the GPU. So it may not be deterministic. You all might get slightly different results. Um, some may be better than the ones I show. Some may not converge. On average, they should be pretty good. So okay. So again, these are just the simplifications we used. Two body, 2D, normalized units where we're going to set mu equal to 1 and pick R1 as 1 is the reference length. We're going to have a very simple case where we're just going to go from R1 equals 1 to R2 equals 1.6. In practice, we'd probably want to make a more general agent where you can learn many radii for the transfer. But this is kind of a simple case here. And then we'll be able to show the delta V at each time step and do some visualization, which is fun. Okay, so the first cell is just kind of a formatting thing. We can skip it, but it expands the width of the cells. So we basically installed these a bunch of standard packages. So basic gymnasium and stable baselines 3 are pretty common for setting up RL environments. We use the actor critic algorithm PPO, which we're not going to go into a lot of detail on, but basically when you're doing a problem, especially a continuous problem, like that's 90% of the time or more, you'll probably want to go to that first. It's convergent. It has good behavior, and is usually the right solution unless you're trying to do something more um, some more fine tuning on how you're setting up the RL. But I think that's as a heuristic, that's a good first place to start. And then we also use a library for normalization where we always normalize our observations and rewards in some standard way, and that kind of just helps the neural network because it's expecting some. It learns better if there's the inputs are normalized. So okay, so we did the installations. The next is yeah, this is valuable to go through. So the next is around our configuration. So our simulation notebook has a bunch of imports, so nothing surprised there. But there's a lot of global parameters we define, and we can talk a little bit about them. So some are just physics parameters. So our time step. I have an epsilon to prevent division by 0 in some cases, and then the mu here is the unit parameter for the gravitational parameter. We just choose mu equals 1. And then, as I mentioned, we go from a radius of 1 to 1.6 for R1 to R2. These global parameters are crashing. So, like, basically, if you go two below zero point 0.7 of your starting radius or more than 2 on the radius or 2 times the target radius, um, we should count that as a crash and penalize it heavily. Um, and then we have some global knobs here for our tolerances. So like basically these are once you get into the target orbit, what's the tolerance to count it as good? Like how close do you need to get the bonus for getting into the target orbit? And we have defined those tolerances for both the radius, the radial velocity, and the angular momentum. And they're pretty generous. You could make them more narrow, but we'd have to do a lot more iterations and it would take longer to run. So we make them generous here so that the it makes it easier to learn, basically. Like once the agent gets into these wider bands, we can find a successful orbit and get a solution that converges. If you wanted to make it much more restrictive, we might not have enough time in the workshop to run it. So there's some trade-off there. Um, but basically, you can set those here. The lower they are, the more demanding you are that you get to the final correct orbit very accurately. Okay, so the next thing is I created this object here, this class to store all our configs. Basically, this is just a data structure that allows us to um, standardize all of the configuration and reuse that and play around with different configs for our training and simulation. So let's just walk through these briefly. I think they're useful to understand. So one is, which control mode, as we mentioned, it's either discrete or continuous. We want to be able to have a config to switch between the two. The magnitude, we mentioned that earlier. This is just what's the maximum burn the agent can do at any time step. Um, so we talked about having a fuel cost penalty. So this is obviously important because we want to minimize fuel. So this is just a float that sets how big of a penalty we get in our reward for using fuel. An ignition penalty, similar, it's just a float which determines how big of a penalty we take for every ignition. And the purpose of this was to have fewer burns. Um, let's see. So there are some other. This is the float, which is just a multiplier on how much we count the penalty due to the errors in energy and angular momentum. Uh, so basically, as you remember, we're trying to minimize the error in energy, minimize the error in angular momentum, um, so that we want to get to the right orbit. Um, Gamma, we talked about this again. So this was kind of the how to discount things far in the future in terms of in terms of your trajectory when calculating the reward. So this is going to be something very close to one. Um, Meaning that we're going to care about the whole trajectory, but we're going to care less and less as we get for long horizons. Um, Success bonus is just a one-time reward for getting in that tolerance region. So this is kind of helps the training process uh, see clearly when it got into the tolerance region. So that's why we have those wide tolerance bands. We get a one-time bonus once we get a trajectory that makes it into those, and then we get a penalty or we get a bonus for staying inside the tolerance region. So this is you know incentivizing just an extra incentive for the agent to stay in the desired orbit. And then there's a few other things here for max orbits, which is basically how long you have to stay there to count it as a success. How many orbits. And then there's some generic PPO, so reinforcement parameters that we define here too. So one is just how many time steps do we do totally for the training. Um, and I'll talk a little bit about that. Actually, that's an interesting one because there's multiple different um, multiple different ideas about time. Basically, um, there's multiple different ideas about time here because there is the time for each trajectory. So like from like starting at R1 to trying to get to R2, you do a simulated trajectory. Um, that takes many iterations. And then there are the total number of iterations you did across all the trajectories. And that is kind of summing up all of those. And that's what we're setting here for training time steps. It's like the total number of time steps you do across all your trajectories in your simulation. So that kind of dictates how long the simulation runs. Learning rate is just the um, optimizer for the neural networks, finding the right weights. And this is basically not something we need to play around with much. And then the entropy. So this is kind of it dictates how much you explore, basically, in your actions. So basically, it makes it harder to converge if you have high entropy here. Um, but you get more exploration of interesting trajectories. You are more likely to converge with lower entropy, but maybe you don't get to explore as much. So there's some balance there. And this final one is just another factor for the continuous only, which is applied to the ignition costs. So basically, um, it's applied here, this equation, but basically it's just another factor on top of what we used for the discrete to penalize ignition costs for continuous. So, okay, so the way all that works, so that was a lot, but that should give some intuition about the knobs we have. But I would say all of these were knobs I chose when setting up this little toy demo. So you could be really creative in the way you choose to create the actions your agent can do, the way you um, choose the rewards the agent gets. And then, of course, once you make all those choices, there's a lot of tuning of these hyperparameters about how you want to um, set all of these things. So there's a lot of choices involved here um, to get the right behavior. So there's two examples. So the reason we did all of this and set up this little schema here for the config is now we can, in a systematic and clear way, define configs to run our training. So we define two configs here. One is discrete, which matches, which is the discrete example, and then one is continuous. And basically, you can just see you change the control mode. You can name them, and there's a bunch of values that I provided for um, the parameters here. Um, So this is how you would define. So if we wanted to define another one, we could just copy and paste this and then choose new parameter values. So now let's go on. Now we've defined those configs for both a discrete case and a continuous case. Now let's go in and look at the physics engine. Um, so here, the physics model we're using. Okay, so we have position and velocity, obviously, in the 2D plane. And there's some acceleration due to gravity. We use Euler-Kromer for integration um, to, given the position and velocity and the acceleration term, we can then determine the next time steps position and velocity. So that shouldn't be surprising to anyone. And then we can of course calculate energy and the polar components as well. So it's pretty simple. We define kind of our two-body physics here, where the real key here is in this time step function. So it takes in the current position, the current velocity vector, it takes in an optional acceleration due to thrust, and then it calculates the new velocity vector and the new position vector given the acceleration. Uh, so basically, and it includes gravity as well, from your central mass with via the mu term. So there should be nothing surprising here. But basically, this allows us to calculate the, t plus one step at every step t. Um, this just converts to polar coordinates. So given an x and a v, it converts to the coordinates that we were talking about earlier. So radius, radial velocity, and then angular momentum. And then we also have a function to calculate the energy um, here. So basically, given the x and v's. So basically, this has all of those observational parameters that we talked about from the slides that our agent is going to look at. You can see that all of that code, all the physics is here, where we can get at every time step, calculate the next time step position and velocity in polar coordinates, as well as the angular momentum and the energy. So now that we've defined the physics, we don't have to spend a lot of time on this. This is just a function to plot the results. So like whether it's our analytical solution or the RL learn solutions, there's going to be a data frame that is spit out with a lot of parameters about the trajectory. Um, we are going to we can just pass that into this plot results and it's going to create a lot of plots. And this way, for every experiment we do, we're going to be creating the same plots so we can compare across. So that's what we do here. We'll see the plots later, so I don't think we need to go into a lot of detail here now. So the first thing we're going to do now is go and look at that analytic Holman solution. So again, to remind everyone, this is analytically solved. We know the delta V1 and delta V2 burns and the magnitudes and the time of when you need to do those burns. So given that we know the burns and we know the acceleration from the delta V, we can use our physics integrator that I showed earlier to actually plot out the trajectories given the analytically calculated burns. So this will do two things. This will show one, that our simulator is working, like our little physics environment we created for this analytically known case. But two, it'll be an opportunity to actually show the Hohmann transfer ideal for this problem. So the way we do that here is this is a method that just calculates the analytically um, uses the analytic solution for knowing when to burn and how big to burn with the Hohmann. And then this next method, again, we're not going to go into a lot of detail here, but basically simulates using our physics integrator the analytic solution, and then we'll make the plots using our plot function. So I think the only interesting thing here, and then it's going to spit out, it has some code to spit out the reports. Oh yeah, and at the end you can see we reuse our plot function. Um, so I think the only other thing to mention here is that I deliberately oversample it a lot. So we don't do a lot of samples in our RL because it would take forever to run for the purpose of this demo. But in the analytical solution, we want it to be very smooth, so we oversample by a factor of 100 here. And the results are shown here. So basically, you can ignore the units, but basically, the key here is that we figure out the right burn, one, the right burn, two, we know the time of the transfer. We know the ideal delta V. so the ideal total fuel used, right? Um, in terms of delta V. And we can compare the theory, meaning the exact analytical case, to what we got from simulation, just to verify that our little integrator works properly. And it does. So, simulation matches theory here, and we can see the plots. So you can see the gray here is the starting orbit, the green is the target orbit at r equals 1.6, and then the blue is our path. So we did the burn starting here, and then we do the other burn here, and you can see the blue basically exactly goes from the R1 to R2 and lines up perfectly with our ideal R2. So there's a few other plots here to familiarize yourself with. The first shows radius versus time. And you can see basically a smooth transfer from our R1 to R2 of 1 to 1.6 respectively. Um, and then we hold at the 1.6. The ideal burn 2 is shown by this orange dashed vertical line. And then our tolerance, if you remember, we defined these tolerances that were pretty wide for what's considered acceptable for our RL. That's shown by the blue band. But basically, this is a nice example showing, hey, look at Hohmann works as you'd expect. Our little physics integrator works, and we get to the right radius. The next plot that's going to be useful for us here and also later in the RL case is the delta V impulses versus time. So basically, how much fuel do we use? What's our change in velocity? Um, as you'd expect, there are two um, there are two impulses here. Um, one at t equals 0, another at the ideal time for the Hohmann, and that's it. And they're both prograde positive burns. Um, and then this final plot shows the cumulative delta V, absolute value of delta V over time. So basically, how big, over, if we were doing a lot of burns, you'd see this continue to rise. And this kind of tells you your cumulative fuel use. And this, so it's a little bit above 0.2 in these units, which is basically what we also see up here. So no surprise there. So this is calculated in our cumulative delta V versus time. Um, all right. So now that we've seen that the analytic solution works, we can look at our RL solution. Um, so how do we do reinforcement learning here? Well, if you remember, we have we define the observation, what our agent sees, the action, what the agent can do, the reward, and that's kind of a complicated, creative thing to define how we want to reward the agent on what it wants to maximize, and then what are the termination conditions for each trajectory? Either it succeeds, it crashes, or it times out because it's spiraling, to far larger orbits and kind of blowing up. So we define those. Again, we have these 6 observations that we give our agent: radius, normalized radius, velocity, radial velocity, tangential velocity, angular momentum and energy, the error in those, how far we are from ideal, and then the previous action the agent did, which helps it does some smoothing by doing that. So again, one of the key simplifications we did among many is that this is the problem is naturally rotationally symmetric. So our policy can be rotationally symmetric, and that simplifies it a lot. It doesn't care where you are in um, from an angular perspective in the plane. It just needs to know these six things. And again, we're going to do a case where it can do either the discrete on-off or the continuous throttle. And we're going to have reward uh, potential based reward shaping using the errors and energy and angular momentum. So basically, the closer you get, the more you reduce those errors, the more you um, are rewarded. And okay, so we have all of that. I don't think so given all of that, I don't think we need to go through all this code. Basically, it's just implementing what I discussed, where basically let's see if there's anything particularly interesting here. Um, Basically, there's some initialization. We are defining the success tolerances. Um, Doing some initialization, starting at R1 and some initial um, velocity, defining a method for what the agent does at every, for what we should do at every step. The first is, interpret the action, apply an impulse, determine the action to do, how big, um, do the physics step, so the integrator, compute the metrics for state, compute the reward. So this is again where there's a lot of creativity in terms of uh, you know, all of those parameters that we define and we'll be able to play around with. But basically, how do you give feedback to the agent that it's doing a good job or not, is defined here. And then finally, when do we decide when to terminate? Which is, did we crash? Are we do our all our success criteria, are they within the tolerances? Have we held the orbit for a long enough time? That's kind of determined here. And then there's some helper functions, which is I don't think we need to go in detail. So given this, we then have some additional shared training and plotting utilities. Um, I think this can be interesting to look at a little bit, but basically, this is the shared training utilities using our library, or off-the-shelf library for the PPO um, policy learning. And then also there's some off-the-shelf normalization that we do. So we use some standard libraries for that. Um, so one thing that is worth noting here is I had to basically we're going to run for the full number of iterations we specify, but your best policy may not be the final one. It might be all we really care about is do we get an artifact where given a state, it's going to give us the best action. So we actually will cherry pick the best one during our entire training process. The last one may not be the best. So basically, at a number of checkpoints, we're going to be saving models, basically, and then we're going to pick the best one, and that's what we're going to show the plots from. So that's kind of, and this is not uncommon because in practice, what you want is the best policy. Um, uh, and you want to take that artifact and then go use it for inference later on to achieve some goal. Um, so, okay, so basically the training is happening here. Um, it's actually pretty simple. It's taking basically we specify PPO. Um, there's a few parameters here where we talked about earlier. These are defined in our little config, the learning rate, the entropy, the discounting from gamma, all of that we talked about earlier. And then, so the training itself is very simple. You just pass it in and use this off-the-shelf library. And then we're going to load the best model and do some visualization um, based on this. And then we'll also print sort of some text output for the final mission report. And that'll include a comparison to the ideal, um, which we calculated analytically, of course. So let's start with the experiment. So this is the exciting part. So for each experiment, we're going to train a reinforcement learn policy from scratch using PPO. We'll evaluate it, and then we're going to inspect those plots and those output diagnostics. Um, so again, training is stochastic. This it is not going to be deterministic from run to run, so we might get slightly different results. There's probably a way to really define a lot of random seeds properly and to get very deterministic results, but I think that's not completely trivial, so I didn't worry about it for this demo. Um, okay, so the first experiment is the discrete case. This is where it's like either on or off, or full prograde, full retrograde, or off. Um, and basically, this will establish the working baseline and kind of is a simple case where it's just learning these discrete behaviors. So we do the training here. We take in our config for discrete that we defined at the beginning of the notebook. We create, this was just one of our, this is just the method we defined earlier to create the training, an object that can do the training for us. And then we train our PPO agent using one of the methods we defined earlier. Um, this is gonna, and then what it'll do is it's actually gonna spit out again the best model, the final model. As I mentioned, those are not necessarily the same, and we'll then produce some plots. So the training took a while, as you recall. It probably took like 5 to 10 to 15 minutes, something like that, depending on the CPU you're using. And we did, and I think the most interesting thing here that I noticed to watch is the rollout success rate. And this is kind of how you can know before you even finish, is your model converging or not within the tolerant with the goal that you set for it. And what success rate here is, th there are batches for the training, and within each batch there could be many trajectories. And then what fraction of those trajectories, those simulated trajectories, end in success? That's what the success rate is. So zero means within this batch of many trajectories, in this training batch, none of them basically succeeded, so that's obviously bad. And as we scroll down, we can start to see success rate increase, and eventually, it's still increasing, so this was a good sign. And then finally, we've hit one. So by the end of our training run, our agent has learned, the policy that we are learning gets basically 100% success in getting to the final conditions within the tolerances we specify. So that's kind of a good example of um, what to look out for if you were playing around and you want to see, hey, is my agent learning anything useful? If it's not, success rate's just going to stay at zero, typically. Um, And okay, so let's scroll all the way to the end. And okay, so basically training is complete, and at the end we load the best model from disk. Um, so the results are shown here. So let's see what we got. Okay, so this table is interesting. This is kind of the mission report, and the ideal is again that analytic Homan solution, which is the final radius is exactly what we would specify. This is the minimum delta V possible, and it's only 2 burns. Our agent um, got to the radius, so that's good. It did not, it was a little bit inefficient, so it took 3 times the amount of fuel compared to the ideal, and it did a lot more burns. And that's not surprising because uh, in our configuration, we actually specified that each burn is quite small because it's either on or off, plus or minus, prograde, retrograde. So each burn is very small, and it doesn't actually have the opportunity to do just one burn and get get to the match the ideal home in here. So that's not surprising, but overall not bad. A factor of three within the ideal amount of fuel. And you can see we get to from R1 to R2, it gets to the correct radius and continue and is stable there. We see some nice plots here for radius versus time. The first, you can see actually it really gets the ideal radius, at least for this run. Um, the radial velocity versus time, again, it actually, let's see, yeah, so again, maybe it's not the exact analytically correct thing, ideal thing, but it's close and within our tolerance. I think the most interesting plots here are actually the delta V and the cumulative delta V. Uh, so you can see one, the maximum delta V in either direction was 0.005. And if you recall from the Hohmann analytic solution, it was like zero point 0.1 was what we really need to do. So it's no surprise we had to do a lot of these small burns to get to the right thing. I would say that the one thing that stands out here is, with Hohmann, ideally both burns are progrades. They should be both positive and in the green. One around here and one around here. The second one happening actually at the orange line. Uh, Interestingly, the agent here is um, learning to do some retrograde burns, which is less efficient. And that's probably where we're getting this, um, factor of three less efficient result compared to the analytic solution. Uh, And then there's some like chattering here back and forth, I think, as it converges, where it's kind of fine tuning, prograde, retrograde with tiny little nudges to get to the right orbit. Um, Here, and then eventually we get close enough and it just shuts off and coasts. So the cumulative burn here, like ideal would have been this dashed line, and again, we're about a factor of three too large. But overall, we got a solution that converged and it's within a factor of a few of what the analytic ideal was here. Um, so one thing that we want to do is see, can we do better if we allow the agent to learn how big of a burn to do? Um, and that's where the continuous, so this is a little bit more complex of a learning problem because it's not just on or off we're learning or forward or, prograde, retrograde, but it's continuous and it's how much do we want to throttle up or throttle down, and that's determined by a float. So we see the same thing. I actually trained it for a little bit longer. I think we did 300,000 time steps last time. We did 500,000 for the continuous. Um, so again, what we would expect is eventually we'll start to see rollout success rate creep up if we are converging on policies that are working and meeting our goals. So it does seem like that it happened here, which is good. And yeah, by the end, we should stick around one if things are working well. Okay, so that looks good. And we probably trained for a bit too long. Like as you can see, about halfway through, we were already converged at one. Um, but in any case, we complete training successfully and load the
Sorry,
best model from disk. Yep.
James, sorry, just to interrupt. One of the attendees had a question because they got very different results without changing, just running the default parameters. Is that
It,
an issue with the CPU dropping out at some point?
so it's actually due to the stochastic nature of the training. So it's not I think that most folks should probably be getting results that converge, but the efficiencies might be different. Um, the It may be in some rare cases it fails, across a lot of people trying it. So again, if we basically, I didn't spend a lot of time trying to figure out how to make it very completely deterministic with the seeding. So that's what we're seeing there. But
One thing to
basically, yep.
one thing
I,
to check is for your run, if at the end, did it actually get to a rollout success rate of 1?
yep. That's right. And if it doesn't, then the other thing is like maybe more iterations would have been necessary to get to a convert like a solution that converges, or maybe you know rerun and try again would be this suggestion. But basically, it's very stochastic, and in practice we'd use a lot more compute to get to a solution that converges, but I was trying not to have the experiments run too long for the purpose of the workshop here. So um, but basically I think most people hopefully can confirm that okay, I see, yes, the run was successful. Cool. Yeah, okay, so hopefully most people were able to get some convergence. But again, the efficiencies might be different because the exact policies your agent learned might be slightly different than mine, or slightly different than others. So here's another case of continuous versus ideal yeah. So again, we have the ideal from the analytic Homan. We compare what the agent results were. Again, the good news is we got the final radius. That's actually not a small, not a small achievement, because it's actually quite sensitively dependent on the reward structure you choose. Um, and so this is good. And here we were actually a little bit less efficient, at least in this particular case, but it's still within a factor of, it's 6 or 7 of what the ideal was. And you can actually see there must have been a lot more burning, because we don't have a nice ellipse. We actually have some weirdly shaped transfer. So this is obviously not perfect. And maybe more time steps, or slightly different choice of parameters could get a little bit better here. But basically, um, this is where that inefficiency is probably coming from here. But again, the good news is we get to the right radius, at least in this run, and get to the right radial velocity. And you can see there's some interesting burn behavior where the roughly, so like basically it's a little bit aggressive in burning and then tries to overcorrect with retrograde burns, and then does another big prograde burn and kind of oscillates back and forth until it gets to the right orbit. So it's doing a lot more burns than we'd ideally want. Um, but again, we were able to at least get a policy that got to the target, fully learned via simulation. And some of you may have better results than this, depending on the random seeding of your particular case. So the third thing we have here is a third experiment, which I want to give you the opportunity to play around and try and do better. So I think in the workshop we have maybe 50 minutes left, if I'm correct. And there's an opportunity here to try and play around with the parameters, and I'll show you how this is done. And we'll kick off an experiment. Uh, so basically, it does take a long time to run, so I don't think we'll be able to do too much live iteration on like trying different parameter combinations. But I think offline you can, and maybe we can get one inside the scope of the workshop. But basically, the idea here would be you can choose continuous or discrete, change some of the uh, reward parameters and the fuel cost penalties, etc., and then rerun it and see if you can do better. So the way to do this, let me go back to the traditional notebook view here. So basically the way to do it is in this cell, um, there you can use this replace method. And what this replace method is doing is taking the configuration you give it and then replacing some of the fields. So basically, you're able to start with, if you remember, there were two configurations at the very beginning of the notebook that I provided. One was the discrete config, and one was, um, and then one was the continuous defaults. And basically, you can pick and choose which things to overwrite. Um, so let's say I want to run a continuous config and overwrite a handful of these parameters. Um, that's what I've done in this my experiment here. Let's see. Let's go back to experiment 3. There we go. So basically, I give it the continuous config. I overwrite the name of it. So now I've named it my experiment. And I want to make, I can choose to do some overwrites here. Um, so I played around with it a little bit. I think it didn't necessarily give better results, but this is just I picked some random parameters. But basically, I think I increased the fuel cost penalty because I thought, hey, since we're using so much more delta V than ideal, let's make fuel more expensive. Let's penalize ignitions more than we did for the experiment two. Um, and then let's allow more training time steps. So went from, actually, this is the same amount. It's 500,000. So, but it's more than the discrete. But you could consider increasing that. But then I actually reduced exploration um, to see if that would help. But again, this is kind of playing around with these things and also change the learning rate as well. Now, I think, let's see, I did look like it converged. I'm not sure if it gave a better result here or not. Oh, not, yeah, so it was a little bit better with these change of parameters again, although there's some randomness. Um, so I got, a factor of 2 to 3 within the ideal. Um, Again, you can see it's kind of a distorted transfer. And you can kind of see the wiggles here in radius versus time showing that. Um, but there's actually less oscillation compared to our plot if we go back up and look at the plot here. So what I wanted to do is have more penalties for burning, whether this um, and more, and also I think there's more penalty with the ignition. If I recall the way I had set it up, there's more penalty for changing from positive to negative. So you can kind of see there's fewer oscillations. So it's these types of parameter changes that are um, tricky to get right. It involves some intuition. And it kind of feels like, as I'm sure you all remember from like chaos, um, it's kind of sensitively dependent on the initial conditions. So as you change these parameters, it's very you might get some very significantly different results based on your choice of the reward parameters and the penalties. So what I would suggest now is feel free to play around with these parameters, increase fuel cost or ignition penalties, or uh, you know, do more exploration. And we'll do one run here, and then see if you can beat the results. And what I will let me see. So I think I shared a survey. So change your parameters now. There's no right answer. You can, um, change them and run this cell. You should be able to kick off your own experiment and see if you can do better, um, given the intuition about what these parameters mean. And when you're done, feel free or feel free not to and feel if you already got a great result, like maybe you don't need to do that. But feel free to go to the survey and paste in your results. So once you have it running, you can go to the survey and you enter your name, your email, and then there's some outputs where you can share from your experiment. So if you look at the bottom of your experiment here, um, there is a your particular configuration was output here. So you can paste that in here, and you can paste in your full output block. So that would be this block here with the mission report. And there's a final field in the survey for any other notes for changes that you made. So, these could be, again, this is a little bit more complex, and you risk blowing up your results. But it is also possible to, for example, go change some of the global parameters and rerun, um, where you go up to the top of the notebook and you can give different crash or success tolerances. So sort of these global knobs. So like for example, if you wanted to experiment with very fine success tolerances, you could change them here. And then you can just paste in those numbers here, to note what changes you made. And then you can just submit. And we can take some questions, if you have any, and then if we get any submissions by the end of the questions, we can review those. Although the runtime is 10 to 20 minutes, so it might take a while.
I might encourage people to use the discrete, which trains considerably faster,
That's a
uh,
great point. Yeah,
so that
that's a great,
so we can compare some tests for the discrete burn.
that's a great point. Yeah. So at this point, are there any questions that folks have, while we run? If not, I'll do my own little demo of changing some parameters and see what we get, as you do as well. Um, so I don't see questions. So let me as you're playing around, I'll explain some of my thinking here. Um, so let's see what happens. So I will change to discrete as Jan suggests, which I think is smart. Yeah. Okay. I'm going to copy this down for reference. Oh, oops, wrong notebook. Okay, so okay. Yeah, so for reference, I just copied the full discrete config from experiment one down here. And I'm going to reuse that, but I'm going to replace some of these. So let's make fuel cost higher. Um, although maybe not that much higher. And I can also make it more, maybe a factor of two. Um, on the ignition penalty, this I don't think we need to even adjust um, because that's only for continuous. I'm not going to change that. Can try fewer time steps, so it'll complete faster. And I'm going to try a larger entropy coefficient. Let's see what happens there if we go up a factor of five um, and not change the learning rate. Um, so now we can watch as the actual training happens. Hopefully, I don't know if this will converge or not. I mean, I made some changes, so we'll see. Um, but we can see if things start to become successful, this will become non-zero. Um, the success rate. And one thing I would point out, so in practice, we're doing this. Okay, so this is good. We're starting to see some success. So that's it's not pathological, really wrong. But so in as you can see, there's all these hype, there's a lot of creativity in defining the rewards and the behaviors of your agent. And then there's a lot of intuition and art in at least in this like one-off workshop of defining the hyperparameter values. Um, and I spent a lot of time with trial and error to get something that works at all with those for the examples here. And that worked fairly consistently across runs. In practice and industry, let's say if you were really doing something RL here, you would just throw a lot of compute at it to find the right hyperparameters. So rather than, fine tuning by hand, doing a lot of iterations and seeing, hey, if I tune the delta V penalty, or I tune this reward or tune this tolerance in different ways, you could imagine just doing a hyperparameter search over wide ranges of those values and actually finding the combination that produces the best artifact, the best agent to get the behavior you want consistently. Um, so in practice, that's the way you would do it. In this demo, it's a little bit more of an art where we're intuiting based on what the agent is doing well and not doing well, what parameters to change to get better results in the next experiment. So this is looking somewhat promising. Although we'll see. Because maybe we do need more timestamps or time steps than 200,000. Because I see we're at 140 and we have a point 0.7 success rate. It'll be close.
One thing is by increasing the entropy, I noticed one of the things to point out is that early on, it's not in the first case you were with low entropy, you're sort of monotonic, right? Your success rate grows up, but as it's catching, it actually sometimes goes down in success rate because of the entropy term. So
That's
it's
a that's a
good for many things, but it also makes the number of trainings usually longer.
that's a great point. Yeah, it makes convergence harder. It can actually unlearn things, basically, that it was doing well before due to the higher entropy. Um,
One thing for our attendees, I'm curious if anyone changed the delta V uh, and see what happens. particularly if you did continuous, right, which again will be slower, but the larger you make delta V, I'll be curious to see how much you get an oscillatory behavior.
Yeah, that's a great point. And also on this delta V, in principle, we handicapped the agent in a way where it can't get to the ideal Hohmann because the max delta V is smaller than what would have been required in a Hohmann, just a single impulse, for experiments one and two. Um, in principle, for continuous, Jan, as you point out, you could make the dV max big and then have the agent learn um, the right magnitude. However, I did experiment a little bit with that, and it's worth trying, but it is also a little unstable because it makes it harder to learn, it seemed, than having a smaller cap and just having to learn more burns than the ideal two. Okay, so this in principle we should be getting some good plots here. I haven't run them yet, but the fact that we're getting success rate of 1 means that it's consistently converging. Um, okay, so I just made the plots. Okay. Um, so I got a 2.3 efficiency. Let's see how that compares to the original um, up here, the original experiment one. And again, there's some randomness across. So due to the non-deterministic nature of the run, so it's a little bit hard to compare one to one. Um, in practice, what you probably need to do is many runs and then look at the distribution and see if you're doing better on average. And if there's a statistically significant better for your one set of configs versus another. But that'd be prohibitive in this workshop, obviously. Okay, so we got a 3.3 efficiency factor for experiment one and a 2.3. So at least for this kind of anecdotal comparison, we did better with some of these changes. And again, I mean, the orbit looks good, and there's some oscillatory behavior, but it converges on the right radius. Okay, so I will again I'll just submit another response. So just to remind folks um, to do that. And basically we can grab the config. So this kind of will show the changes in the configs that I did for my experiment. And you can paste it in here and then paste paste the output block as well with the results. Cool. So I'll wait a few minutes as folks complete. Please do mention in the chat if you are having any success or failures. Um, and also do mention if you have any trouble accessing the survey. We can actually look. I think right now we've only haven't gotten any responses yet, but only ones are the two that I submitted. I'll try another just as we wait for a few others to complete. So maybe taking Jan's suggestion and trying the delta V with continuous. Um, I'm gonna grab just for reference these continuous defaults here, and then to change to continuous, all we have to do is do that, and I think we can leave. Let's leave everything the same. Actually, you know what? Let's do a bigger fuel cost penalty. We'll double it, and we'll also double the ignition penalty. Yeah, that's good.
Well,
Um,
there's the question on submitting the results in the folder. You should have a link to the Google Slides. The last Google Slides contains a link to the Google form. I I decided not to take my advice and do continuous, and it'll be close to whether I finish by 4:30.
got it. Got it. It's taking a long time. Yeah. That's yeah,
But I'm doing continuous with a very large delta V max and seeing if it can actually learn it.
that'll be interesting to see. In my offline experiments before, I found it was a little bit harder, as I mentioned, to get the convergence. But in principle, let's do. I think delta V max or mag is you can kind of see what it would require based on the if we scroll up based on the analytics solution. You know, we have two burns of a bit above zero point 0.1. So in principle, having something above some range above that will give it the option to actually learn something close to the ideal. Although I think it is hard to converge on that. So maybe I'll do this.
Has anyone gotten theirs to finish?
Sounds like people are still running. Uh, so let me just since we're all training, I can give a little bit. Oh, I see someone commented they've completed. Yeah, it'd be great to submit in the 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 survey if you're able to get access. Um, I think I just sent a link in my in someone asked about how to submit in the survey, so I just sent a link, which I think if you haven't accessed yet, you can do there and just submit your results directly. Um, so and just while folks are doing that, since we're all doing some training, I can just give some a little bit more intuition about what's happening with the PPO training. So again, this was was an actor critic method where the actor is the policy, which is that pi of A given S. So it's given the state, what action should I take? Um, And the critic again was that value function is a function of the state, which is how good is this situation um, in terms of the reward. And the way that the training works is um, we take the current policy we have and predict the action, give it to the simulator, the environment. We and then we use that in the environment to measure how good or bad each action was. So the critic predicts the expected outcome, which is the V of S of sub t. And then we compare to what actually happened. So the based on what the actor said to do and what the environment said happened, our um, physics environment. And then we can calculate the reward of what actually happened. And we can look at the difference to measure basically what the advantages of was if there was an action that was done by the um, agent that worked better than was expected, or was worse than expected. And then we update the policy accordingly, whether it's doing better or worse. And the over time, the value function, the V, is also updated in this training loop. So basically, we're kind of training these two networks simultaneously to learn the actor function and the critic function. But for the purposes of for our purposes, they're really just black boxes. Okay, got it. I see we have another response from Paul. So that's cool. Let's see, individual. You can take a look. So I see what Paul did. So let's see. It looks like a continuous, um, and just for comparison with continuous, just to remind, it looks like same fuel cost, bigger, um, bigger ignition penalty. Is that right? Yeah. So bigger ignition penalties. Um, the change in reward shaping, and then fewer time steps, more entropy, and change in the learning rate. Interesting. Oh, so nice. So it looks like given this plus a little bit of randomness, Paul was able to get a better result than I was able to show. So here we got an efficiency like a efficiency of 1.69. So now we're within a factor of two with Paul's results of the Hohmann ideal. Obviously, it took a lot more burns still, and maybe it did converge to an orbit within our tolerance, but it wasn't exactly the right orbit. But it was very efficient in terms of compared to the other learned results we've had. So nice job, Paul. So mine is about 70% done. And this iterations per second is CPU dependent really. And just for reference, typically what I would see with if using a CPU notebook in the collab, I was usually getting around like 300 to 400 iterations a second. Using the TPU instance, which I think probably has newer CPUs on it. Um, you can get about 1,000 iterations a second, it looks like, at least for the instance I was granted by Google. And then I was able to do faster. I developed these notebooks running them locally on my MacBook with an M2. And there I was getting something like 2 to 3,000 iterations a second. So that was actually a little bit faster for playing around to figure this out. So it is possible as well to run these things locally. You don't need to use the cloud. There is the option to do um, GPU GPU training too. It's a moderate um, modifications to the code, and you can specify like CUDA. However, the overhead of doing that seemed to be bigger than the speed up when training the network with GPUs. And overall, I didn't really see much improvement or potentially actually um, a regression in the iteration velocity when using GPU. So that's why we're using CPU here.
Can I ask
Okay.
if anyone had their run completely fail, as in the success rate never got beyond zero? Because you can set your parameters so that it never finds the right thing.
And in fact, it can be easy, easy to end up with a set of parameters where it never finds the right thing. So it would be interesting to hear if folks have run into that. So as you know, as people are still experimenting, we can talk a little bit about what the next steps would be to improve this further, right? So this is a very simple case, and to make it really practically useful, you'd want to improve it further. And I had mentioned some of them during the course of the talk, but to summarize, one, you could imagine doing this with multi-body systems and complex 3D geometry. The modeling, as you can see, the modeling approach would be similar. The simulation and modeling, RL modeling would be similar. The observations you let the agent make and the actions you let the agent make would need to be more complex, obviously. So there's kind of more degrees of freedom, so to speak, in terms of what the agent would need to be able to do. Maybe you have um, directional burns, for example, among other things. But you could add a lot of complexity there, make it 3D, put in multi-body, do more complex orbits, Earth, Sun, Mars systems, for example, where there's different where the bodies you're transitioning to are also moving. So you can find all that physics, and then the modeling process is the same, just with more complex modeling, more complex observations and actions. So like that would be one obvious upgrade. Although you can see it's a bit tricky to get the right parameters for convergence. So that's where the second, I think, upgrade would be, where we would do that kind of hyperparameter search. So we wouldn't be like doing one off in a Jupyter notebook to train it. We'd actually create that more complex agent behavior and environment, and then use a lot of compute to find the right set of rewards setup and hyperparameters that enable us to train an agent to get the right policies to navigate that more complex problem. Um, so that would be, another thing to do. Um, I think there's other optimization. I mean, there are other things we could do in terms of oh, Jan, I see you've raised your hand.
And finish the thought. It was actually a continuation of that.
Oh, got it. I think there's other things we can do in terms of ran increasing the randomness of our simulated trajectories. So again, I really wanted to constrain it because as you can see already, the runtime is needed to fit within the workshop. But in practice, you could imagine having a variety of and randomizing the start and end radii and velocities and many other parameters to make the agent more robust. So like for every trajectory it simulates, it would be simulating it with different initial and final conditions and goals, and it would learn a more robust set of policies um, as a result of that. So like I think that would be another thing. But all of these are, are big increases in complexity and compute. I don't know if that was your point, Jan, or if you wanted if
No,
you had.
what I was going to say is that as you add slightly more complex physics, for example, you add the finite masses of the Earth and Mars to it. One interesting strategy would be to instead initialize to start with the Hohmann solution. And you know the solution once you add object masses will not be Hohmann, but it starts you in a position that's a little better than random. That gives you a slight head start in figuring out the solutions. You do want to keep the entropy away from zero because it won't, you know, you run the risk that the Hohmann solution is already good enough and it stops when you really want more precision than you get.
That's a great point. So yeah, so you can actually provide known trajectories that are good to the training process. So I did not do that here, but because for this simple case, it'd be kind of cheating. Like if we gave known Hohmann solutions to the agent, I felt like, hey, this is a little bit too much like cheating because we're basically trying to have it learn the Hohmann. Uh, ex- but if you have more complex dynamics and you have some approximate or some analytic solutions that work for that, or at least some cases of it, you can provide those examples, and that's absolutely right. That's absolutely right. And probably a good idea rather than starting from scratch with all of, just random trajectories. Um, let's see. I'm not sure if we have any other responses yet that'll beat Paul, who
Anyone else
had.
close? I'm at 80%, but I'm still at zero.
Oh no. So I
So
think,
I
yeah.
I will have a failed. I did crank up my DV max perhaps too much to give it too much freedom. I think I used zero point 0.3 delta V max instead of 0.02.
Got it. Yeah, the conversions can be hard with that. So I actually, yeah, that reminds me, I can check on mine. So I did a 0.15, and I think it's done now. And it does look like it's not, it does look like it's converging to something that works.
Okay.
So let's take a look at what we get there. Okay. Let me scroll down. Oh, I think I need to regenerate the plots.
Yeah.
Oh, okay. Okay. So that is an interesting one. Okay, so this is, yeah, so it has this kink. So obviously very strong burns. Um, and it's very inefficient. So it did it's a factor of 10 worse than the ideal. So this is kind of cool to show like you make some changes in the parameters and you can get, order of magnitude changes in efficiency. So even getting to within a factor of 2 to 3 is pretty good. Although I think compared to any of the other examples, um, we did
The
we did a
burn
lot
penalty
for
really helped it, right?
the
It
burn
did.
penalty. Yeah. Oop. So we got down to 49, but they're just big burns, so lots of fuel. And you can see actually, so it is actually hitting, having a big it burns too much early. It learned to burn too much early. Really, you just need one time step. It should just need one time step at about a bit above zero point 0.1, but obviously it does more than that and then overcorrects, and um, that's why you get the kink. But I think these are some cool results. Yeah, maybe I'll submit that one just for completeness.
So I'll say we'll stay on for another 4 or 5 minutes, but I do encourage people to submit the results even after we close um, the meeting because it'll be really cool. And since you've already done most of the work to get the results, uh, it's worth seeing how well you do. Um, and will they be able to see the other results?
We could make it available.
Yeah,
Yeah.
maybe we'll put it on the like the summary of it because it'll be interesting for you to see to get that intuition to see as people change different things what things worked and what didn't work.
Yeah. Yeah. So please do um add in your results offline if they don't finish in the next 5 minutes. And then we'll make it available. I'll figure out how. Jan, maybe I don't know who the best to circulate to the group is, or what the best way to communicate that is. But basically, we can make the admin page here, or something similar to it available where
What I was
folks.
thinking was to make the summary of the range of values, just create a PDF of that and put that
Oh, got it.
on the Google because the Google Drive is accessible to all participants for the whole year. So you'll be able to come back to it. So putting it on the Google Drive is a good way to share with everyone.
Got it. Okay. I
Maybe
can
we'll
maybe.
maybe anonymize the names just so that your names isn't you know particularly linked, but we can put the results in so you can see what the parameters and what the output was. It looks
Yeah.
like I'm still 7 minutes away, so I'll post mine afterwards.
7 minutes away, but still it's 0% or zero
Oh, I haven't
success.
checked. It's still scrolling down. I did increase the number of iterations. Uh, so
Yeah, that can help too. Although sometimes if it I
yeah,
think it starts to converge on some bad policies, and sometimes it never recovers. So even
yeah,
if
it's still at zero. So mine will be a fail, but we'll see.
got it.
Are there any
That's a
well,
good data point as well, though. That's a good
yeah,
example.
don't do this. Uh,
Mhm.
while we're finishing up, are there other questions either about the ideas behind reinforcement learning or this specific example and extensions to it?
Or even more broadly, any in the last 5 minutes, either questions on the lecture or questions on I mean one other area I can talk about is the applicability of the physics education and research experience you get from doing a PhD and postdocs, and how that translates in industry and what my experience has been there. So I'm also happy to chat about that because I presume a lot of the audience is in the academic sphere here. So happy to give some context on how my transition was. I will say that it's a very powerful background. Um, I've been, as I mentioned at the beginning, working in industry doing machine learning and AI. Not really reinforcement learning in my job, but other types of AI. For almost a decade now after graduating from Brown physics with a PhD, and I think that the physics education is a tremendous advantage compared to many others. I think it's only going to increase with the advent of AI. I'm sure a lot of you are using AI for code and for other technical questions. Um, it's incredible how fast it's improving. Like the newest models are and Copilot coding agents are able to speed people up by 10 times, 100 times, 1,000 times um, on really complex projects. Um, so the physics background's always been super helpful for being able to understand data in a more fundamental way, I think, than many others with other backgrounds in industry. And then being able to communicate about it is tremendously valuable. And I think my intuition from using these tools a lot, AI coding and the trajectory of the way AI is going, I think the physics background is only going to be even more powerful compared to things like, a lot of people, for example, in software do computer science or have traditionally. I think the way that you use agents to code and solve problems is very similar to mentoring a more junior graduate student, for example, where they are doing work and it's technical work, and you may not look at every line of code they are writing for their analysis, but you understand the fundamental principles and what the goal is and what a good result should look like and what plots to generate to see if things are behaving the way you expect and how to interpret it to if they're not, and how to you have this person doing some work product, and then you can interrogate the output based on what you would expect it to look like. That is something, or even in your own work when you're doing complex analysis and simulation work in physics. I'm sure a lot of you have had this experience where there's bugs in your code or there's issues you learn based on the fact that they're not behaving as you expect. That type of interrogation of this black box that's doing work for you, I think is very, the physics education translates very well to what I think the future of work will look like with AI agents. So this is a bit of an aside from this talk, but I think you'll all be served well with your physics background. Um,
So I'm going to close with an aside that I got to 135 for a cost, just to give you a sense. And if you look at the solution, it's a sine wave. It's basically still correcting the at every cycle it is correcting burning, overburning, underburning, overburning, underburning. So clearly I didn't set enough penalty for the amount of burns, and I let it burn so much that it so yeah, the fuel penalty was not high enough for uh,
and that's an interesting. So it gets to around R2, but then does some oscillatory behavior.
correct.
Yeah.
Yeah,
Okay. That's
I had set the fuel penalty too low, and so it didn't hurt it to get to R2, overshoot R2, undershoot, overshoot, undershoot, and it just kept doing that. And that's the best solution it found. So
got
I'll
it.
post that after.
That's a cool solution, and it's illustrative of the sensitive dependence on these choices of parameters, and it's kind of it does feel a bit like some sort of you know black magic in terms of figuring out the right sense, the right combination of parameters based in intuition. But again, this is why throwing a lot of compute and doing a big hyperparameter search is probably the right way to go if you were doing it for a real problem. But cool. So I think we're at time for the
Yep.
2.5 hour slot for
And
this. But I want to
yep.
thank you all for your attendance and questions and in working through the slides and the experiments with me.
And post the solutions. Um, Thank you, James. This concludes our Brown AI Winter School. Congratulations to everyone. And we'll see you all next year with 7 or 6 new plus one repeat module, uh, studying new things in AI. Thank you all. And thanks, James. See you.
Thank you.